One of the craziest things about blockchain is that you have open access to a brand new permissionless financial ecosystem, where if you can find, value sitting out there on the blockchain, as a blockchain developer, you can just leverage your technical skills to capitalize on that value. And there are developers out there who are making millions, literally millions of dollars with something called front running on the blockchain. Okay, so you might have heard of this. And if you haven't, you're going to learn exactly what front running is in this video and how developers are making so much money with it. You're going to learn exactly how to do front running in this tutorial with Solidity, with smart contracts on the blockchain in the real world. And so if you're new around here, hey, I'm Gregory. On this channel, I turn you into a blockchain master. So if that's something that you're interested in, then smash that like button down below for the YouTube algorithm and subscribe to this channel. And if you like everything you see in this video today and you want to take the next step and really beef up your coding skills so that you can become a blockchain master, then definitely head on over to dappuniversity.com/bootcamp to get started today. Let's dive into a full tutorial on how to do front running on the blockchain. So real quick disclaimer, in this video, I'm mostly going to show you how to do this technique so that you can understand how it works, that you can be an ethical auditor and protect yourself from front-running attacks. I'm not making this video in any shape or form so that you can exploit different DeFi protocols out there. But if you're trying to become a good blockchain developer, then you need to understand how this works so that you can protect yourself and also protect others. So definitely use the information that I'm showing you today for good and not for bad purposes. So I'm going to invite my assistant Victor on to do this presentation today. This is actually an excerpt from our blockchain mastery program, and I've opened this up as a free sample for you to see what it's like to work with us to learn these advanced blockchain concepts. And so if you like what you see in this video today, then definitely click that link down below for more. All right, so with that being said, let's jump into it.
We will start by discussing what front-running attack is, and then we will move to creating contracts that are vulnerable to front-running attack. We'll perform a transaction, then we'll simulate an attacker that sees the transaction in the mempool and then front runs it. And we'll do all of that in Hardhat. So if that sounds interesting, let's get started. So in this video, you'll learn about what is front running as a concept. Then we'll learn how to perform front running attack. And to do so, along the way, we'll learn a lot more stuff, like we'll write even assembly code while we develop the victim, the vulnerable contracts. We'll learn how the mempool works, what is the mempool, and in general, to perform this type of attack, you need to learn how the blockchain works. So we'll also review some basics that all of us probably know about the blockchain, but we have to know them deeper to perform this type of attack. And of course, this is for educational purposes only. We will never ever suggest or advise performing this attack. This is just for the auditors out there to learn on how to write safer and more secure Solidity code. So without any further ado, let's get started. So we will do this front-running tutorial inside Hardhat, as we've done all of our tutorials, or most of them. So to start in Hardhat project, just do npx hardhat, and then you'll get a file structure like so, which is composed by the contracts. You're not going to have these two folders at first. They are generated after you compile the contracts you've developed in the contracts folder. And then we have node modules. These are all of our node modules, and I'm just explaining this so everyone is on the same page. Then we have the test folder. This is the folder where we'll write all the tests for our contracts. We have a getignore file that just ignores all the files we don't want to push to GitHub. Then we have the Hardhat config file. This is where we'll configure the network, the local host, or any other network like Guerli or the mainnet. Then we have a package.json file. This file specifies all the dependencies we need installed for this project to run. And finally, we have the readme file where we'll usually write some documentation about the project itself. So first things first, I've already written down the contracts themselves. So let's start. We have two contracts for this tutorial. We have a factory contract and a wallet.sol contract. Let's start by explaining the factory contract. So I'm using any Solidity version greater than or equal to 0.8.13. That is fine. We are using one of the latest versions or a more recent one. Then we have the factory contract here, and we have a wallet owner mapping, and we basically have a scenario and architecture where this factory contract will deploy wallets. And for this factory contract to do this, we have two other functions, which are create wallet and deploy wallet. So the create wallet function, all it does, it takes in a salt. This salt is then passed to the deploy wallet function when the deploy wallet function is called in the create wallet function. And the deploy wallet function, as you can see, it returns an address of the instance of the wallet it deployed, and we want to save that wallet in this wallet address that we are returning here. Then what we are doing is taking the instance of the wallet interface, and we've imported the wallet here, and this is our other contract that I'll explain later. It's just a wallet contract. We're passing in the wallet address that we got from the deploy wallet. So whenever we deploy the wallet, we've deployed the wallet, and then we're taking its address of the deployed wallet, putting it here. So we're making an instance of the contract, and then calling the initialize function with the message.sender, with the person that we want to initialize it with. So we can see so far how this is looks like a regular contract, not vulnerable to attacks. We are just deploying a wallet and initializing it, and oftentimes you need to initialize contracts whenever they are upgradable because they do not have constructor if they're using the delegate proxy pattern. And we've made more in-depth videos about upgradable contracts, so you can check out those. But that's the long story short. You need to initialize contracts that do not have constructor, which usually happens when you want to develop and deploy upgradable contracts. Let's see what the deploy wallet function does. So it takes in this salt. So why do we need the salt in the first place? So we need the salt because the way we are deploying a contract, a wallet, is by using the create to opcode. And the create to opcode, in our case, this is an opcode, but in this case we are using a function, the create to function. And this function is only available in YUL, and YUL is an intermediary language between Solidity and raw bytecode. So it's something lower, it's a low level programming language than Solidity. Solidity is very high level, and YUL is created for us to maybe whenever we develop the contract, if we want to have more control and do some low level stuff like we are doing now. And we have even made a tutorial about YUL a few months ago. So what happens here is, first we are checking that you don't have a wallet already. This is just some logic. Usually contracts would do this type of bookkeeping. So we have the wallet owner, and we're saying, hey, this message.sender, if we check in the wallet owner mapping, his address needs to be 0. It can be any other address, because if that's the case, then you already have a wallet. So this is like a guard. It's not an if statement, it's a guard. We're guarding against this. If that passes, then we want to take the type, the wallet type that we imported above, and say .creation code. And this will give us the bytecode in bytes, and we'll save this as memory. And the compiled bytecode, it's basically the contract's constructor function and all the contract's code. And in regarding to that, just as a side note, there is creation code and there is runtime code of a smart contract. And these are two different pieces of bytecode that are associated with a smart contract. And all a smart contract is when it compiles to bytecode, so it's easier to be understood by the EVM. And contrary to that, the runtime bytecode is the bytecode that is executed when the smart contract is called. So when you want to interact with a function like the deploy wallet or create wallet, the runtime bytecode is ran. But we don't need it, we need the creation code. And we'll need the creation code whenever we want to deploy here. So in the create2 function, it takes an argument that is the bytecode. We'll have to add some padding to the bytecode. That's what we are doing here with the add function. Then we have mload. Mload loads the bytecode. Then we have salt. We're passing in the salt, and the salt is just some random value from the user. And 0 didn't mention, but 0 is just the first argument, which is how much ether you want to send in the transaction. We don't want to send anything. And this create2 returns an instance. And then if we check if the address is not 0, if it's 0, then this failed. It should be not equal to 0. And then we'll just do some bookkeeping and add the instance to the mapping. So basically, long story short, we are just deploying a new contract by using create2 and passing in this salt value. Let's now check out our wallet contract. So our wallet contract has this ownable contract that it inherits from, and this is because we want to have the only owner modifier. So we want to have some access control mechanism in the wallet itself, because this is a wallet that you personally use. Then we have the IERC20 contract imported from OpenZeppelin and the safe ERC20. We said we want to use the safe ERC20 for IERC20. Then we have the iBalances mapping that just tracks your balance that you have of different tokens, both Ether and ERC20 tokens. And you will see how this is done later. Then we have a state variable. So all a contract is a behavior. So it has some behavior that is made from these functions, from the contract's functions. And then we have some state, and the state is with these state variables. Oftentimes we'll have a mapping in a contract. It's very common to have a mapping. And we have this bool state variable. So then we have an initialize function. This is what we called when we deployed this contract here, or after it's deployed, I should say. So it's called here. And we should pass in the owner, because as you can see here, we're using the transfer ownership function from the ownable contract. And we're saying, hey, we want to transfer ownership of this contract to this owner. And we're saying initialize should equal true. And if it's already initialized, we shouldn't allow this to happen, this transferring of ownership. Then we have a deposit function, and this is public, as you can see, and it's payable. Public means anyone can call this once the contract is deployed on the blockchain. And payable means you can send Ether inside. First you specify the token you want to send, and then the amount. The token can be either 0 or some address of an ERC20 token. If we are sending Ether, the address will be 0 because Ether does not have an address. Only ERC20 tokens do. So whenever that is the case, we'll update the balance and we'll say, hey, this 0 token will just append the message.value you've sent. And the message.value is a built-in variable that is basically the amount of Ether you've sent in this function. Or if it's the other case where the token is not equal to 0, the token address, then we'll perform a safe transfer from this contract, which is an ERC20 contract, or a token, I should say. This is an ERC20 token. We want to safe transfer from the message.sender, the person who called this function, to this contract, this amount of tokens. And then we'll just update your balance here. Finally, we have a withdraw function. This withdraw again takes in an address, the address of the token you want to withdraw, and the amount you want to withdraw. And notice this time this is a public function, but it can be only called by the owner because of this only owner modifier that is imported from this ownable contract that we inherited. And the withdraw function, if the token again is 0, then we'll perform a transfer by using the call method, and we'll just say message the sender call, and we want to send to him this amount of tokens, and we require that this transaction is successful or then it failed to send ether. So the call function, how it works, because it's a low level function, it returns a return value indicating if the call was successful. If that's not the case, then we'll move to the else block where we access the token and say save transfer from your account this amount of tokens. So we'll just transfer this amount of tokens to the caller of this function. And we already know that you are the message.sender, that the owner is message.sender because of this only owner modifier. So that's pretty much it. These are all the contracts. Let's now jump to the test itself. So whenever you compile the contracts, you get these two folders. You have an artifacts folder where if you go into the contracts, you can see our two contracts. If you go to the wallet, you'll get the wallet.json file, which is the ABI for this contract. And the ABI for a contract, it's just the interface. It just shows you all the functions you can call of a contract. So that's what we are taking into here. We'll need the wallet contract ABI. We're also requesting the chai and the Hardhat library. Finally, we have a describe block, and this describe block it groups a lot of tests inside, so you can put as many tests as you want. And this contract has 4 accounts: the owner, person who deploys the contract, Alice, which is a user, an attacker, and the factory contract itself. Before we run any tests, we want to run this before block, where we get the signers, get all the accounts. So this test itself, it's run on the localhost network. So we'll deploy the contracts themselves on a localhost network, and we'll also run this test, run everything, call the function on the test network or the Hardhat network. And then we want to deploy the factory contract, and we do so by getting the contract factory, then connecting the owner to this contract factory and deploying it, and getting an instance of the contract here that we initialized, declared here first. Then we have our it block where we perform the front running exploit. How do we do this? So first we get a salt. How do we get the salt? Well, we get this string, then we say 2UFT 8 bytes, and then we hash this. That's how we get this a salt. Then we say factory.connect Alice, and then Alice wants to create a wallet with this salt. And what happens here? Where is the front running attack? So the thing is, any transaction needs to go to the mempool first before it can be put into a block. And this public Ethereum mempool can be seen by anyone because it's public. And the Ethereum mempool is basically a collection. That's where all the pending transactions are waiting to be confirmed by miners and added to the blockchain in a block, and then the block is added to the blockchain. So whenever a user initiates like a transaction on the network, it's first broadcasted to all the nodes on the network and added to the mempool of each node. So each node has a mempool of its own, and all of these individual nodes compose the public Ethereum mempool. And all the transactions that have higher transaction fees are usually prioritized because of the higher transaction fee. And this public Ethereum mempool can be monitored by attackers, and this is where front-running attack comes in. And a front-running attack, explained simply, would be type of a blockchain attack where an attacker, a malicious user, attempts to profit by intercepting and executing a transaction before it is confirmed on the blockchain. So front running basically exploits the transparency and the public nature of the blockchain transactions, which allow anyone to see the pending transaction in the mempool. So whenever an attacker monitors the mempool, and if he identifies a transaction that is in the mempool that is a profitable transaction, he submits just a higher free transaction with the same destination address and basically it's same everything, but with higher transaction fee. And basically that's why it's called front running. He front runs the profitable transaction that he saw in the mempool. Because he paid a higher fee, the attacker's transaction is prioritized by the miners and added to the blockchain before the original transaction, resulting in the attacker receiving the desired outcome before the original transaction is executed. And this oftentimes, in this case, or at least it will block the deployment of the contract Alice wants to make. So we are just getting all the transactions here in the mempool. Then these are all the transactions. Then we want to find our transaction. Then we want to send the transaction with more gas. You can see we're adding gas here, gas price and gas limit. We're adding more than the transaction we found. Then we mine all the transaction. We can do this manually. And after all of that is done, we check to see if the wallet owner is the attacker address here. We can see, we check if we expect that the wallet is initialized, so the wallet initialized equals true, and we expect that Alice doesn't have now a deployed contract in the factory contract. We can see that by using the wallet owner mapping, and if we pass in his address, we should get on the other side an address 0, and that confirms that we've successfully performed a front-running attack. So, and to perform this, you have to, in the Hardhat configuration file, you have to say mining, you have to say networks, you have to have Hardhat. Whenever we use Hardhat, we want to say mining. That is not automatically, it's done manually. Or if it's done automatically, the interval is 1000. And finally, if we run the test by doing npx Hardhat test, you can see the test is passing, which means we have successfully performed this attack. So how can you mitigate this bug? Let's talk about this. So if we go to the factory contract, scroll up, we'll see that we are using create2, and this is the main problem with this approach. Create2 is using a salt, and this salt is supplied by the user. So this is wrong, that this salt is supplied by the user and can be seen in the mempool, and this is how the front running was made possible. What we should make is make a hash of the message.sender and a nonce. So message.sender plus a nonce should be equal to some, we should hash this, and then this cannot be front run. Why? Because message.sender is a variable hard-coded in this deployed wallet, and the nonce is again some random value, but because it is hashed with the message.sender and you cannot front run the message.sender, you know who sent the transaction, but because it's hard-coded, it's put into the transaction, this hash, and it cannot be replicated. So this is why this solution would work. So that's pretty much it. That's all I had to share about front running and how to perform a front running attack. We've learned a lot about what is front running, how to perform front running. We have learned what is the create2 opcode. We've learned how to develop both of these contracts, the factory contract and the wallet contract. We've learned how create2 works, and we've learned how to prevent front running attacks from happening and still using create2 opcode.
All right, so that's an overview of how to do front running on the blockchain. So I hope you like this video. As always, smash that like button down below for the YouTube algorithm. Subscribe to this channel if you haven't already. If you like this video, you want to take the next step, you want to get advanced blockchain skills so that you can change your career, break into the industry, increase your salary well past 100K, I can show you to do that over at dappuniversity.com/bootcamp. You really don't have to be an expert to get started today. I've helped people with zero coding experience become real world blockchain developers in a matter of months. So that's all I've got. Until next time, thanks for watching Dapp University.